So here you are given three different circuits. One with an alternating voltage applied across a resistor, next is applied across capacitor, next applied across an inductor. Suppose the EMF equation is the same in all cases. Okay, the equation of alternating EMF is the same. Can you quickly tell me how much will be the current in the resistor?
I is equal to V by R, sir.
Okay, tell the complete equation. So if you just divide E by R, what does it become? Okay, it will simply be E naught by R sine omega t. The EMF function and the current function will have the same phase. Okay. Next, can one of you tell me the current equation in the second case? Isha or Pradyun, can you answer? Okay, fine. Through the capacitor, the current will be leading the EMF. Okay. The peak value of current I naught will be E naught by XC, where XC is 1 by C omega. And phase, if you observe, it will be the phase of EMF plus an extra pi by 2, because current will be leading the EMF in case of a capacitor. Next, in case of an inductor, the current through the inductor, peak value will be E naught by XL, where XL is L omega, and the phase of current will be pi by 2 behind the phase of the EMF. So sine omega t minus pi by 2. So just by looking at the EMF equation, you can write off the current equation if only one of the elements is present, either R or C or L. Okay. Now let us look at it in reverse. In all three of these elements, let's say the current equation is given to you. Assume current is written this way. I is equal to I naught sine omega t. Or let's make it more general. Let's add a phase also here. Omega t plus phi. Some constant, phase constant. Same current in the second case. And also in the third case. Okay. Now tell me the equation of voltage across the resistance. Voltage or EMF, okay, across the resistance. How will you write it? Rishi, what will the peak value of voltage be?
Sir, I naught.
Peak value of current is I naught. What will the peak value of voltage be?
I naught by.
I heard someone saying E naught. You should not just write it as E naught. You should write it in terms of what is given here in the problem. Like basically from the current equation, how to write the voltage equation is what we are doing now. Okay, tell me, how will you calculate I naught across a resistor? Suppose EMF is known. How will you find out the peak current I naught?
Sir,
Huh.
so I is equal to E by R.
So I naught will be equal to?
Then we'll get an equation, and then I naught will be whatever the peak value. uh,
You can tell what the peak value. I naught is E naught by R. Okay. If I naught is E naught by R, This is the peak value of current, no? Then E naught will be I naught into R. E naught will be I naught into R. So we'll write that here. And we know the current equation. We are now expected to write the voltage equation. Across a resistor, the alternating current and the alternating voltage will be in phase with each other. So whatever is the phase of the current, same will be the phase of the voltage function also. Sin omega t plus phi, you can write as it is. So if you know the current equation, you can write the voltage equation. That is what I am trying to tell you here. This becomes E naught value. I naught R is E naught in this case. Okay. Next equation or next situation, you know the current through the capacitor. You have to write an equation for voltage across the capacitor. Tell me, how are peak current and peak voltage across the capacitor related? How are I naught and E naught across a capacitor related? Okay. I naught is E naught by XC. So E naught becomes I naught into XC. This value is the peak current in this case. So E naught becomes I naught into XC. That's the peak value of EMF. And in a capacitor, we know current will be leading the EMF, means EMF will be lagging the current. So the phase will be written like this. The phase of current function minus pi by 2. Because current has to be leading, that means EMF will be lagging. So we'll subtract pi by 2. Next, inductor. In an inductor, we know I naught is equal to E naught by XL, where XL is L omega, inductive reactance. So you can write E naught is I naught into XL. So the voltage across the inductor becomes I naught XL, where XL is L omega, can be calculated. What you are left with is the phase. This value is the peak voltage. In case of an inductor, current will be lagging the EMF, means EMF will be leading the current. So the phase of EMF will be the phase of current plus pi by 2. Simple. So from voltage function, you can write the current function. From current function, you can write the voltage function also. Is this clear to all of you? Isha, Pradyun, understood?
Yes, sir.
Okay. Now consider an LCR series circuit. Means LC and R, all three of them in one loop, connected in series. Just a moment. We'll place a resistance here, a capacitor here, an inductor here, and an alternating EMF source. Order is not important, whether it is LCR or RCL or CLR. Okay. Assume the EMF equation is known to us, E naught sine omega t. So let's use some simple basic ideas first. There are three elements connected in series, and that series combination is connected across a voltage. So basically what should happen, whatever voltage is there, E naught sine omega t, it should get distributed among these three. So there will be some voltage across the resistor, there will be some voltage across the capacitor, and there will be some voltage across the inductor. The algebraic sum of these three, VR, VC, VL, should be equal to the EMF at any instant. Okay. Suppose this EMF is some 10 volts at a particular value. Time to time, it keeps changing. Let's say it is 10 volt. Then when you add these three, it should become equal to 10 at that moment. Okay, obviously it should be. Total voltage across that branch is 10. So sum of all voltages should be equal to 10. That's fine. But you see these three elements connected in series. In any circuit, if there is a set of elements connected in series, tell me what will be common to all of them. If there are some circuit elements connected in series and you switch on the circuit, what will be common through all those elements? Consider a simple circuit like this. Two resistors R1, R2 connected to a DC voltage. Okay, constant voltage. What can you tell about this circuit? Or what all can you find out about, in this?
Then we can find the resistance.
We can find the effective resistance. Okay, good. What else?
And then we can find the voltage also.
Voltage is already given to you. Know? Which voltage are you talking about? Okay, what else? Can you tell individual voltages across these resistances?
Yeah, sir.
How?
Like, wait, no, I don't think so, sir. I don't think so.
Okay, can you tell how much current flows in this loop? Fine, fine. Just listen to what I'm saying. I don't know. Maybe people are in holiday mood or something. We can find out current. Why not? And if some circuit elements are connected in series, be it resistors, capacitors, inductors, or a combination of those, okay, through all the elements that are connected in series, the current will be the same. In a particular branch of a circuit, the current has to be same everywhere, because we assume steady state has been established. There's no accumulation of charge happening anywhere. Okay, so at any point in a branch or in a circuit, inflow of current should be equal to outflow. Therefore, whatever current flows through the resistor here, the same current should flow through the capacitor and also the inductor. It's a rule. Okay, in a single branch, the current has to be same everywhere, because if current varies from point to point in a single branch, it means at a particular point, inflow of current is more than outflow. Means charge is getting built up there. That is meaningless. I mean, that should not happen. Okay, we assume steady state has been established. There's no buildup of charge happening anywhere. Okay, so all these circuit elements now, circuit components, should have the same current flowing through them. Fine. So in an LCR series circuit, the current will be same through all three elements. Our aim now is to derive an equation for that current. Okay. So this is one thing you need to remember. The algebraic sum of voltages at any instant should be equal to the total voltage that you apply. Next, in a series combination, or in a series connection, I should say, we are not combining anything. All the elements, by elements I mean resistors, capacitors, inductors, okay, will have the same current passing. This is the main idea in AC circuits. Okay. We now have to derive an equation for this current. And based on the equation for current, we can tell how much is the power dissipated. When current passes through a resistor, power will be dissipated. Okay, we'll talk about all those things. Now, if an alternating voltage is directly applied to a resistance, you get a current in this form. Resistor will try to keep the current in the same phase as the EMF. Okay. If an alternating voltage is applied to a capacitor, you get a current of this kind. what does the capacitor try to do? It tries to make the current lead the EMF. And if you apply an alternating voltage across an inductor, inductor tries to make the current lag the EMF. Okay, so one of them tries to keep it in phase with the EMF, keep the current in phase with the EMF. The other tries to make it lead the EMF. The third one tries to make it lag the EMF. Now, if all three are there, then what will happen? You have to include the effects of all three of them. So on the whole, what will happen is the current will neither be exactly in phase with EMF, because it's not only a resistor, no, the other two are also there. Resistor will try to maintain zero phase difference. Capacitor will try to make the current lead the EMF. So it will make current have a phase of plus pi by 2. Okay, it will try to do that. Inductor will try to make current have a phase of minus pi by 2 compared to EMF. So all three will show their effect now. So on the whole, what will happen? The current may not be in phase with the EMF. The current may not lead by pi by 2. The current may not lag by pi by 2 also exactly. Okay, so we have to give weightage to all three of them while calculating the current. Okay, now the problem here is that this EMF E naught sine omega t is not applied only across the resistor or only across capacitor or only across inductor. It's applied across the combination. So the problem here is that we don't know the individual EMFs that appear across them. You can't say 1/3 of this, 1/3 of this, 1/3 of this will appear. That is meaningless. Okay, in a simple connection of two resistors itself, the distribution of voltages will be in the ratio R1 is to R2. Okay, you can't say equal distribution will be there. Fine. So we don't know the voltage across each element. We don't know the current also. Okay, so we have to use some techniques here. Listen, the idea, as I said, is that the current will be same in all three of them. Let it be. What does the resistor try to do? It tries to keep the current in the same phase as the EMF. Capacitor tries to make it lead. Inductor tries to make the current lag. Therefore, the effective current in this case will be somewhat like this. You observe the previous equations. If it's only resistor, it's E naught by R sine same phase as the EMF. If it's only capacitor, it's E naught by XC sine phase of pi by 2 extra. If it's only inductor, E naught by XL, some phase of pi by 2 lesser. Okay, so in all three cases, all three currents, the difference is in the denominator. What denominator? That resistance or reactance. Okay, that value will vary from element to element, and the phase value will vary from element to element. Fine. So here we have EMF equation E naught sine omega t. Then the current equation should be of this form. E naught. Okay, that's the peak value of EMF taken as it is. Divided by something should be there. If it's only a resistance R, if it's only a capacitor XC, if it's only an inductor XL, but when all three are there, we should divide E naught. I mean, E naught will get divided by something. At least dimensionally to be correct, E naught should be divided by something. Then the phase will be something extra. It could be 0. It could be between 0 and pi by 2. It could be from minus pi by 2 also. So it can vary. That phase constant that you add, okay, this phi naught value that is being added could be anywhere from minus pi by 2 to plus pi by 2. If it's only an inductor, it's minus pi by 2. If it's only a resistor, 0. If it's only a capacitor, plus pi by 2. Now all three are showing their effect. So it could be anywhere between these values, minus pi by 2 to plus pi by 2. So what we effectively have to calculate now is this denominator Z and this phase constant phi naught. Okay, so if the EMF equation is of this form, then the current equation should be of this form. And in the current equation, there are two unknowns. Fine. Now, let's apply KVL to this loop first. Assume the current is I, EMF is given to you as E. Let's start from maybe this point and move clockwise. The first element we come across is the resistance, and we see that we are going in the direction of current. Can one of you tell me how to write potential change across a resistance?
So VR will be minus IR.
Correct. Minus IR, because we are going in the direction of current. Next, how to write potential change across a capacitor? Because the next element we come across is the capacitor.
Capacitor I forgot, but inductor is minus LDI by dt.
Okay. Isha, Pradyun, how can anyone of you recollect and tell how to write potential change across a capacitor?
Minus of the charge on the
Correct. First plate divided by C. So assume charge on the plate, left side plate is Q at a particular instant. Then you will write minus Q by C. Rishi, remember this, okay? In a capacitor, Q is equal to CV, so V is equal to Q by C. But when you apply it in KVL equation, it will be negative of charge on the first plate divided by C.
Okay.
Next, voltage across inductor, as you said, minus L di by dt, because we are going in the direction of current. Done. And the last element we come across is the AC source itself. So plus E should be equal to 0. We return to the starting point. Okay. So in this equation, if you observe, there is charge Q, which is a variable. Charge on the capacitor will keep changing. And there is current. Current is dq by dt. So there is Q term, there is a dq by dt term, and there is di by dt also, derivative of current. That means d square q by dt square, second derivative of charge. Current is the first derivative of charge. Derivative of current will become the second derivative of charge, and there's a constant also. So this is a second order differential equation. You don't actually have to solve this equation. It will be quite complicated. But remember the solution. So what do we not know about the current here? We don't know the Z value, and we don't know the phase constant phi naught. Okay. So what you can do here is consider three vectors. Okay, we actually call them phasors because they are arrows which represent phase. They're not actually vectors. We are just drawing arrows to represent the phase of some quantity. So they're called phasors. One phasor, which means one arrow, will represent the resistance. Now resistor, what does it try to do? It tries to keep the current in the same phase as the EMF. No. So it tries to maintain zero phase difference. Capacitor tries to maintain, it tries to make current lead the EMF. Inductor tries to make current lag the EMF. So first, draw the XY axis and mark the angles like this. First phasor we consider will be that of the resistance. Now resistance tries to maintain zero phase difference. So we'll draw a vector of magnitude R towards the zero direction. Okay, we'll draw an arrow of magnitude R towards the zero direction. This is R. Next, what does the capacitor try to do? Capacitor tries to make the current lead the EMF. Leading means plus pi by 2. So we'll draw an arrow of magnitude XC. Okay, capacitive reactance towards the plus pi by 2 direction. And inductor, what does it try to do? It tries to make the current lag the EMF by a phase difference of pi by 2. So we'll draw a vector of magnitude XL towards the minus pi by 2 direction arrow. Okay. Using this phasor diagram, we can find out both Z, that's the unknown denominator of E naught, and the phase constant phi naught. Now what we need to do is we need to get the resultant of these three vectors. Now if there are two vectors, you can use triangle law, parallelogram law, one of them to draw the resultant. But if there are three, it becomes slightly complicated. There's an extra step you need to take. You can observe that the vector corresponding to XC and the vector corresponding to XL are exactly opposite to each other. Okay. One of you tell me, if there are two vectors like this, one of magnitude, let's say 25 units, another one exactly opposite to it of magnitude, let's say 13 units, how much is their resultant? And in which direction is it? Two vectors opposite to each other, one of magnitude 25, the other of magnitude 13. How much is their resultant?
12, sir.
12. In which direction?
Towards the right.
Towards the 25 vector. Okay. Now there are two ways to write the resultant. You can say the resultant this way is 25 minus 13, that is plus 12. You can also say the resultant in this direction is 13 minus 25, that is minus 12. It's the same thing. A vector of 12, 12 units to the right is same as minus 12 units to the left. Okay. So it does not matter which vector you take first. Resultant in the direction of that vector will be that vector's magnitude minus the other vector's magnitude. Now here what we are going to do, we need the sum of these three vectors, XC, XL and R. Since XC and XL are exactly opposite to each other, we'll first simplify them. We'll first get their resultant. And then we'll bring R into the vector addition. So XC and XL are exactly opposite. Then we can say that their resultant, okay, the combined effect of XC and XL will be in this direction. See, if I'm favoring the direction of XC, how should I write the magnitude of this vector? Should I write XC minus XL or XL minus XC? If I want to write the resultant of XC and XL in the upward direction, how much will it be?
XC minus XL, sir.
It should be XC minus XL. So this is equivalent to something like this. XC minus XL. And the other vector is R vector. So we wanted to add three vectors. Since two of them were exactly opposite to each other, we took advantage of that and found their sum first, their resultant first. Now we'll add this resultant to the third one. And since there are only two vectors to be added now, we can make use of the parallelogram law of vector addition since their tails are joined. And these two vectors are mutually perpendicular. So the parallelogram you get will be a rectangle. Automatically it will become a rectangle. Okay. And how do you draw the resultant using parallelogram law of vector addition? The diagonal drawn from the common tail to the opposite end, opposite vertex. Okay. Now these two vectors are perpendicular to each other. One vector's magnitude is XC minus XL, the other one's magnitude is R. Then the resultant's magnitude, this resultant is what we take as Z. That's what we were looking for. And it will obviously be equal to root of XC minus XL whole square plus R square. Okay. So the denominator of E naught can be calculated that way. Now, how we got that result is from this, by solving this second order differential equation. Actually, theoretical proof is that. Okay, but you don't need to understand, or you don't need to know that proof. You can directly remember the phasor method to calculate Z value. Okay, so what is the phasor method? You draw three vectors. Since they are not actually vector quantities. See, resistance is not a vector. Fine, it's a scalar. But we are assigning it some direction. So we are just using some arrows to represent the phase. So we call them as phasors. Draw three phasors. One of magnitude R along the 0 direction. One of magnitude XC along the plus pi by 2 direction. The other of magnitude XL along the minus pi by 2 direction. The resultant of all of them, or the magnitude of resultant of all of them, will be the Z value. Okay. So Z becomes square root of XC minus XL whole square plus R square. If you write XL minus XC whole square also, it's the same since you are squaring it. Okay. Next, there was one more unknown. We didn't know the effective phase constant, or not phase constant also. We didn't know the effective amount by which the phase of current leads the EMF. Now we got the resultant of XC, XL and R. Okay. This Z value, whatever phase angle, okay, whatever angle the Z vector makes, that is the effective extra phase of the current compared to EMF. Or that's the phase difference between the current and the EMF. Now let's go back to the triangle. Which one? This one. This is called the phasor triangle. Just a moment. So this vector is XC minus XL. This vector's magnitude is R. So the triangle that you get by drawing these three vectors, XC minus XL, R, and their resultant Z, that triangle is called the phasor triangle of an AC circuit. And you need this angle phi naught. The opposite side to phi naught is XC minus XL. The adjacent side is R. So you can say tan phi naught is equal to XC minus XL divided by R. That's all. You got the phase angle also. And not only tan phi naught, you can write cos phi naught. Cos is adjacent by hypotenuse, R divided by Z. You can even take sin phi naught if you are comfortable with that. Opposite by hypotenuse, XC minus XL divided by Z. Okay. So that way you can get the, what do you call? Z value. Z value is called impedance. Net impedance of the entire circuit. If only resistor was there, you call it resistance. If only capacitor was there, you would have called it capacitive reactance. If only inductor was there, you would have called it inductive reactance. If all three are there, you call it impedance. Okay. Of the circuit as a whole. That is how it is calculated. And phi naught is the phase constant. And look at the phase constant equation. Tan phi naught is equal to XC minus XL divided by R. Basically, what is happening here? It's an LCR series circuit. All three of them are trying to show their effect. Fine. Suppose only R was there, L and C were not there. Okay. Just a moment. Let me copy this circuit. Tan phi equation, tan phi naught equation is XC minus XL all divided by R. First case, if only resistor was present, okay, we call it as a purely resistive circuit. Okay, no capacitor, no inductor. If there are no capacitor and inductor, we take XC to be 0. You don't take C to be 0. Remember this point carefully. If there's no capacitance, don't substitute C as 0. You should substitute XC as 0. And if there's no inductor, XL will be 0. So in that case, what does tan phi naught become? You get tan phi naught is equal to 0 minus 0 divided by resistance is non-zero. So the whole thing is 0. One of you quickly tell me tan of what angle is 0? In the range minus pi by 2 to plus pi by 2, tan of which angle is 0? I think I should call it domain. In the domain minus pi by 2 to plus pi by 2, tan of which angle is 0?
0.
0 itself, tan 0 is 0. So the phase constant becomes 0. And Z value, Z you know is under root XC minus XL whole square plus R square, right? If XC and XL are both zeros, this becomes equal to R itself. Okay, that is what happens if the circuit is purely resistive, if only resistance is present. Next case, let's take a purely capacitive circuit. Means only C is present, R and L are not there. Okay. So if it is purely capacitive, first tan phi naught. Tan phi naught is XC minus XL divided by R. XC is non-zero, numerator is non-zero, denominator is 0. So this tends to plus infinity. Tan of what angle tends to plus infinity? In the range minus pi by 2, in the domain minus pi by 2 to plus pi by 2. It will be pi by 2. Tan 90 degrees is infinite. Okay. So, and we had derived this before also. If alternating EMF is applied directly to a capacitor, we know current will lead the EMF by a phase difference pi by 2. So this equation also tells us the same thing. And the impedance in that case, root of XC minus so if it's a purely capacitive circuit, means R and XL will be 0. So XC minus XL whole square plus R square. In this case, Z becomes equal to XC. And we know already the current equation will be E naught by XC sine omega t plus pi by 2. So as expected. And you can easily tell what happens if it's a purely inductive circuit. When do we call it purely inductive? R should be 0, XC should be 0. Then in that case, tan phi naught XC minus XL divided by R. So it's like negative something divided by 0. So this tends to minus infinity. And tan of what angle is minus infinity? Minus 90 degrees. So minus pi by 2. So phase constant becomes minus pi by 2. Or the phase difference between current and EMF becomes minus pi by 2. And impedance effectively will be under root XC minus XL whole square plus R square. R is 0. Becomes XL itself. Okay. Now, even if any two of them are there and the third one is not present, the procedure will be the same. Suppose resistor, capacitor are there, inductor is not there. Take XL as 0. Simple, you'll get the current equation and all. Okay, let's solve problems based on this now. So let me just briefly tell you once again. Suppose LCR combination is connected and an EMF, alternating EMF is applied across that combination. The only thing you will need to find out, only two things you'll need to find out are the denominator of the E naught value, which is basically the impedance of the circuit, and the phase constant, phase difference between the current and EMF. And to do that, we make use of the phasor diagram. Okay. Just a moment. Let's say EMF equation is given to you like 200 sine 100 pi t. Okay, let's take an equation like this. 200 sine 100 pi t. Resistance assume is some 80 ohms. Capacitor, I'll not give you the exact capacitance value, but XC, okay, this is R value is 80 ohms, or fine, let me write it here. Let's say XC is also 80 ohms and XL is 20 ohms. Okay, you can like XC and XL values depend on the actual capacitance and actual inductance. You know, XC is 1 by C omega. Omega is fixed here, 100 pi. But capacitance, like it depends on the capacitor that you are using. So based on that capacitance, let's say XC is this much, XL is this much. Okay, so all necessary information is given to you. Derive the current equation. It has to be of this form: E naught by impedance and the phase value, whatever is there. Or okay, E naught also I can substitute now. Sine 100 pi t plus some phase constant. Calculate these two and the current equation will be obtained. Do this quickly, all of you, and type your answers in chat. How much is Z? How much is phi naught? Okay. Isha, any answer for Z? Impedance of the circuit. Can one of you tell me the formula for Z?
Sir, XC minus XL square plus R square.
We'll tell under root.
Oh, under root. Yes. Sir, is it 100? The answer.
Z will be 100 ohms in this case. Root of 80 square plus 60 square becomes 100. And
So
tell me,
tan phi I got 3 by 4, but I don't know what
okay.
time.
Okay, let it be. You can write tan inverse 3 by 4 also, nothing wrong in that. Now tan phi is XC minus XL by R. So 80 minus 20 divided by R is 80. 60 by 80, that is 3 by 4, correct? So you can just write tan inverse 3 by 4, but tan of 37 degrees is 3 by 4, so you may use that also. Therefore, the current function becomes 200 by 100, that is 2 sine 100 pi t plus 37 degrees. You can write it like this, or you can just write tan inverse 3 by 4. Isha, is this clear?
Yes, sir.
Okay. Pradyun, did you get these values? That is 100 and tan phi is 3/4. Oh, okay. Okay, fine. So see, it's quite easy to derive the current equation. If you know XC, XL and R and the EMF function, you can easily write the current equation, not a big deal. Now let us think of what all can be derived based on the current equation. We know they all have the same current. So yeah, if we know the current equation, what can we tell based on that? Fine. We had already discussed that today itself. If you know the current passing through the resistor, you can tell what is the voltage across the resistor. If you know the current passing through the capacitor, you can tell what is the voltage across the capacitor only. And similarly for inductor. So in an LCR series circuit, we had that problem. We didn't know what is the voltage across each element separately. VR, VC, VL were not known. One thing we were sure of is that the current will be same in all of them because they are in series. So what we did now is we derived the current. Once you derive current, you can write expressions for voltage across the resistor, voltage across the capacitor, and voltage across the inductor. These can be derived. Okay, let us do that in this problem itself. I'll copy this circuit, or actually these values are what we need. Fine, let's copy both. And the current equation we got is I is equal to 2 sine 100 pi t plus 37 degrees. Okay. The same current will pass through all three of them. We can take advantage of that and derive the voltages. Can any of you tell me how to write voltage across the resistance now, based on the current passing through it?
Minus IR.
See, minus IR, no. Minus IR is the change in voltage across a resistor when you move from one side to the other side. So right now that is not what we want. We just want the magnitude. Okay. Now you may say IR, that's fine. But think in terms of what you learned in alternating circuits. If you know the current flowing through a resistor, okay, you write the voltage across the resistor this way. Peak value of current is I naught. Then peak value of voltage will be I naught multiplied with R. And then resistor keeps the voltage in the same phase as the current. So whatever phase the current function has, same phase the voltage function also will have. Okay, so think in these terms, not in terms of IR Q by C minus LdI by dt. No. So we know the current equation. We need voltage across the resistance. It will be I naught into R sine whatever phase the current function has, you take the phase as it is, same phase or equal phase. I naught is 2 here. How much resistance did we take? 80 ohms. 2 into 80 becomes 160 sine whatever phase the current function has, take it as it is. That is the voltage across the resistance at any time. I told you, no, whatever voltage you apply here, whatever is the source voltage, all of it won't go to the resistor. Only some part will appear across the resistor, and the part that appears across the resistor is this. Okay. Next, voltage across the capacitor. Isha, can you try to answer this? Okay, Isha is not there in the meeting. Pradyun, if you can unmute, you tell. Otherwise, Rishi, you tell the answer. Okay. See, we need a peak value and the phase. That's the only thing you need to find out in AC circuits. How to get the peak EMF across capacitor based on current? If peak current is I0, how much will the peak EMF be?
E0, sir. And then
No. You are not supposed to call it E0. You have to express it in terms of I0. So,
sir, ICXC.
Current through the capacitor multiplied with XC. Correct. So now current in all three of them is the same. So you don't have to call it IC. You can just call it I or I0, peak value of current, multiplied with capacitive reactance. What am I writing? I0 into XC. And what about the phase? Current phase. Okay. Tell me this. Capacitor makes the current lead or lag. Current will be leading or lagging. Capacitor makes current lead the EMF. Means the EMF across the capacitor will be lagging the current. So you'll have to subtract a pi by 2 from it. Therefore, it becomes I0 is 2, XC is 80. So 2 into 80 is 160 again. Sine current phase is 100 pi t plus 37 degrees. From that, you have to substitute pi by 2. You can express the answer in degrees or in radians. It's your choice, that phase value. Okay. So this will be the voltage across the capacitor as a function of time. Next, the third part, voltage across the inductor at any time. Rishi, tell me the peak
Sir,
value.
I into XL.
I0 into XL is the peak value. Sine. What about phase? What does an inductor do in terms of phase?
Plus, sir, it leads. So will be plus 5.
Tell clearly, what leads what?
Sir, the inductor leads by pi by 2 angle.
The EMF leads current by pi by 2.
Yeah.
Okay. So it will be current phase plus pi by 2. So I0 into XL. I0 is 2, XL is 20, 2 into 20 is 40. Sine. The phase of the current function is 100 pi t plus 37 degrees plus 90 degrees now. That will give you the voltage across the inductor at any time. Okay. Let us check if the algebraic sum of these three at a particular instant is equal to the applied EMF or not. It should be. Okay. Let's take t equal to 0 itself. If you put t as 0, first you can observe that the applied EMF becomes 0 at t equal to 0 because sine 0 is 0. So I'm just checking if E is equal to VR plus VC plus VL or not. So first case, randomly I took the time as 0. At t is equal to 0 seconds, EMF becomes 0. Next, voltage across the resistor. If you put t as 0 in this, how much does it become? 160 sine 37 degrees. Okay, let it be 160 into sine 37 degrees is 3 by 5. Okay, that's the voltage across the resistor. Next, voltage across the capacitor. T as 0. Sine 37 minus 90. Sine theta minus pi by 2 is minus cos theta. So minus cos 37. So minus 160 into cos 37 is 4 by 5. Okay, that's the voltage across the capacitor. Next, voltage across the inductor at that moment. T is 0. So it's like sine 37 plus 90. Sine theta plus 90 is simply cos theta plus cos theta. So it becomes 40 cos 37. 40 into cos 37 is 4 by 5. Fine. Let's see, does this become 0 or not? 160 into 3 by 5. Fine. Minus 160 into 4 by 5. And this 40 into 4 by 5 can be written as 160 into 1 by 5. 40 into 4 is 160, no? So I'm taking it as 160 into 1 by 5. So we have a 160 into 3 by 5 here. 160 into 1 by 5. So they both together become 160 into 4 by 5. And this cancels it. So VR plus VC plus VL is 0 as the EMF, okay, equal to the EMF. You can substitute any time and check. The algebraic sum of these three will definitely be equal to the applied EMF at that instant. Random, I mean, we just checked that t equal to 0, but you can take other times also. You can take a half time period, 1/4 of time period. Time period is 2 pi by omega. Half of that is pi by omega. You may substitute that time and check. You will get.
Sir, but checking with 0 is one of the like more convenient, right? Because
But see, it should always hold, no? So you have to check with other values also, and you check it. Your what do you call? Retention will be better. You'll remember these ideas better. You substitute other angles or other times and check for yourself. You'll remember the ideas better. Okay. So based on the current function, we are able to tell the individual voltages across the resistor, capacitor, inductor at any time. Good thing. If you can tell the individual voltages, you can tell the RMS voltages. Obviously, individual voltage function, if you have, RMS voltage function is not very difficult. So let us generalize all this. Try to follow this carefully. This is the important, I mean, most important part of LCR circuits. So if you have an LCR series circuit like this, and you know the EMF function, E naught sine, whatever be the phase. Okay, let's just take it as omega t simply. Then we first write the current function like this. I is equal to, okay, not even the current function. We first calculate impedance like this, under root XC minus XL whole square plus R square. Then we calculate phase constant like this. Tan phi naught is XC minus XL whole divided by R. Once you know these two values, you can easily write the current function. I is I naught. What is I naught? E naught by Z. And since EMF is a sine function, current also will keep as the sine function plus the phase constant that you get from the formula, tan phi formula. Okay. So now you know the peak value of current, I naught. And you know the total phase of current. Let's call it as phi 1, the whole thing. Then you can write voltage across resistor, capacitor, inductor. If you write voltage across resistor, it will be I naught into R. Okay, some phase you will get. Whatever is the phase of current, same phase you will get for resistor. Observe the peak value of voltage across the resistance, I naught R. That is E naught by Z into R. So peak value of voltage across resistance is E naught by Z into R. And it's a sinusoidal function. Tell me, for the sine function or the sine equation, how much is the RMS value?
sine or sine square, sir?
For the sine function itself, how much is the RMS value?
0.
RMS, why will it be 0? Root of mean of square. Average is 0. Okay. Try to
2
recollect
by
this.
pi, sir. 2 by pi.
2 by pi is the average of the positive half cycle. Suppose you have something
Oh,
like
yeah.
this. What is the RMS value of this function?
E0 by root 2.
For sine function, it is 1 by root 2. If it is multiplied with E0, it becomes E0 by root 2. Correct. Now here we have the voltage across the resistor as a sinusoidally varying function. We know its peak value also. From this we can tell voltage across the resistor RMS value will be E0 R by Z root 2. Just the peak value divided by root 2 becomes the RMS value for any sine or cos function. Okay. Next, voltage across the capacitor is I0 into XC sine of phase of the current function. Now capacitor makes current lead, means voltage lag. So minus pi by 2. Okay. That means peak voltage across the capacitor will be I0 is E0 by Z into XC. And that also means RMS voltage across the capacitor will be E0 XC by Z root 2. So you need to remember how to derive all this. You don't have to remember the final formula. Remembering so many formulas like peak voltage formula, RMS voltage formula, impractical. Final exam, you may not be able to recollect properly. Okay, but think of how we got all this. It's all based on the current function. From current function, you write the voltage function across any element. Then you derive the peak value, RMS value and all. This requires a little bit of practice. You have to, whatever we derive today, you have to derive all that once on your own. You should be able to do that on your own whenever necessary. Then you can solve any problem in alternating current. Okay. The entire chapter, the crux of the chapter is in this lecture only. Next, voltage across the inductor. We know it is I0 XL sine of phase of the current function. Now inductor makes current lag, means voltage lead. So plus pi by 2. Okay, I'm also writing equations based on that only. I remember some basic ideas in the chapter. Based on that, I derive. Even if I'm solving an exam question paper, I do the same thing. So peak voltage across the inductor becomes I0 is E0 by Z into XL. And that would make the RMS voltage across the inductor equal to E0 into XL divided by Z root 2. Okay. Now RMS voltage across capacitor inductor are not of much interest to us, but RMS voltage across the resistor is useful. Why? As current passes in an LCR series circuit. Okay, just a moment. Let me copy this diagram. As current passes in an LCR series circuit, whatever be the current, let's say I. One of you tell me, when current passes through a resistor, what happens?
So can you repeat your question?
When current passes through a resistance, what happens?
Sir, the current decreases like due to.
So you should not say current decreases. The resistance will already show its effect, would already have shown its effect and made some current flow through it. Due to the flow of current through a resistor, what happens? Pradyun, if you can answer in chat also. What happens when current flows through a resistor? Flow is opposed. Okay, that is what a resistor does. It opposes the flow, battery drives the flow. They both come to an understanding and make some current flow through the circuit. Due to that, what will happen? Heat, correct. Okay, Rishi, when current passes through a resistor, heat is dissipated. Resistor converts electrical energy to heat energy and gives out to the surroundings. Means it will remove energy from the circuit. Okay. Then capacitor inductor. Now see, when current passes through a capacitor, no, charge on the capacitor could increase which means energy stored in the capacitor will increase. And if current flows the other way, charge could decrease, means energy stored in the capacitor decreases. But capacitor does not produce heat. Fine, it can store energy, it can give back the energy to the circuit. It doesn't dissipate it in the form of heat. Similarly, an inductor. When current flows through an inductor, magnetic energy gets stored in it. And when current decreases, that magnetic energy also decreases. So inductor also stores energy and gives it back to the circuit. Capacitor, inductor, they don't dissipate energy. Resistor dissipates energy from the circuit. Okay, so you can calculate something called power dissipated. Means the power given out from the circuit, and the only element which dissipates power is the resistor. Keep this in mind. Now tell me, okay, I'll write it here. Only the resistor dissipates power. The other two just store energy and give it back to the circuit. Resistor converts electrical energy to heat energy and wastes. Okay, not waste. Sometimes that is what we want. So that in that case, it's an advantage. Otherwise, it's a waste. Okay. One of you tell me the formula for power dissipated by a resistor. General formula.
I square R.
Okay. You can use I square R, or you can use V square divided by R. Now, current through all of them is the same, so you don't have to particularly specify, but voltage is different across each element. So in this case, in an LCR series circuit, or when resistor is combined with some other element, you have to take the voltage particularly across the resistance and square it and divide by R. You can't do this EMF. You can't assume this EMF is applied directly to the resistance. No. Okay. You can't take the EMF E. You have to find out the voltage across the resistor. Based on that only, you can tell what power is dissipated by it. So let me write it clearly. Voltage across the resistance squared divided by R. Okay. Now it's an AC circuit. Current will be varying. Voltage across the resistor also will be varying. We derived elaborate equations for all of them. Okay. From time to time, they keep changing. Therefore, the power dissipated also keeps changing. And we'll be interested in average power dissipated. And for average power, you use the effective current in the circuit, which is the RMS current. So you can write it like this. I RMS squared multiplied with R. That's the definition of RMS current, no? RMS current is something like the constant current which would have caused the same effect. Okay. So you can write it like this, or you can even calculate it like this. Voltage across the resistor, its RMS value, square it, divided by the resistance. So if current is constant, it is I square R. If current is variable, in place of I, you take the RMS value of I. And same with voltage. Okay. And current IRMS across the, or IRMS value is I naught by root 2. We all know this. I naught is E naught by Z. So it becomes E naught by Z root 2. Therefore, the average power dissipated in an AC circuit, we have to square this first. E naught square by Z square into 2. Okay, that is IRMS squared multiplied with the resistance R. Okay. We can write this as, now 2 can be taken as root 2 into root 2. So I'll write this as E naught by Z. That is I naught. Or wait, E naught by Z root 2. E naught by Z is I naught. Divide by root 2 becomes IRMS into another E naught by root 2. E naught by root 2 is ERMS, RMS value of the voltage. And what will you be left with? R by Z. And from the phasor triangle, this one, R by Z is nothing but cos phi. So we can write it as IRMS cos phi or cos phi naught. Therefore, average power dissipated is RMS current, RMS voltage, cos phi naught. This cos phi naught in an AC circuit is called a power factor. Okay, next class we'll solve problems based on power factor. We'll discuss something called wattless current. Okay, all those things. Fine, we'll stop it here for now. I'll send you the notes. Like it may take around half an hour or something, but derive all these equations. So where do you start from? Take an LCR series circuit. Assume some voltage is applied across it, alternating voltage of this kind. Write the current function first. Okay, in the current function, first things you need to know are Z and phi naught. Once you know that, you know the current function. Then with the current function, what all can you do? You can tell voltage across resistor, capacitor, inductor separately. You can find out the RMS voltages. You can tell the power dissipated, average power, instantaneous power, all those things. So do this derivation once, then the concept will be clear. You'll be able to solve any problem from this chapter. Okay, fine. Thank you all. We'll continue on. When will the next class be? Thursday.